one of these two screens is not actually yellow. If you don't believe me, look, my close-up camera here, Google sent me the Pixel 3a. Let's get really close to it. It consists entirely of red and green pixels. So how is that tricking my camera into displaying it as yellow? It's a good question, because your eyes do exactly the same thing. When I look at that screen with my eyes, it looks yellow. You can be a great photographer without understanding how color really works. But if you're the type of person who wants to understand the mechanics of photography, I'm gonna dig really deep and get really nerdy about color. So first, let's talk about what color is. Color is wavelengths of light. Some light travels on long wavelengths, another light travels on slightly shorter wavelengths. That's it. Light doesn't know what color it is. Light just has a frequency and a direction. The human brain is what assigns it color. Why? Because if you just had a bunch of data about, oh, I'm catching light that's in this frequency range, you wouldn't be able to handle that. So your brain simplifies it for you and assigns colors to certain wavelengths of light. But it gets a little more complex than that. Let's start over. Light is just photons, and photons have many different wavelengths, most of which we can't see. So this line represents all the possible frequencies of light, with short frequencies over here and long frequencies over here. How short and how long? Over here we have 0.00000001 meters, which is very, very small. And over here we have 10,000 meters, which is 10 kilometers or like 6 miles if you're American like me. So pretty long. Photons can travel at lots of different frequencies. Visible light lives in this tiny space here in the middle. Down here we have gamma rays, X-rays, ultraviolet, and on this side we have infrared, frequencies used by radar, FM radio, broadcast TV, shortwave radio, and AM radio gets the longest frequencies. And yet it's just this little part here that you can see. So why is it that we can't see gamma rays and we can't see AM radio? We could, theoretically, our eyes could have adapted to pick up those sorts of frequencies, but they didn't, because we don't want to be gathering information that's not useful to us. If you could only see really, really long frequencies of light, well, that stuff passes through buildings. That's why your radio can work from inside your house, and thus your house would be invisible. Oh, you'd only be able to really see Earth or other things that would block those really long frequencies. The really short frequencies like gamma rays and X-rays, they don't head through the atmosphere. So you wouldn't be able to see anything at all unless you walked around with like an X-ray flashlight shining it on things. So our eyes adapted to see this tiny range of visible light because it's those frequencies of light that are long enough to penetrate the Earth's atmosphere, but short enough to bounce off of things that we might want to navigate around or eat or avoid. Other creatures live in different environments like underwater, and they might pick up slightly different frequencies because those are more useful to them, because different frequencies penetrate water than penetrate the air. So let's talk just about that visible light spectrum. Now, let's get into here. Let's zoom in. We're just going to expand this one particular area. Down here we have the purples, then we get into the blues, then we have greens, and then over here we have reds. I didn't draw yellow because I don't have a yellow marker. So now you know your eyes are sensitive to only very specific frequencies of light, and they catch different frequencies and assign them this broad range of colors that we call the visible light spectrum. And we have that because it helps us walk around the Earth and find food and stuff. So let's talk about how our eyes catch that light, because it's almost exactly the same way cameras work, and it is useful to know. First, the front of your eye is a lens. It focuses light onto the back of your eye, and it's the back of your eye that actually catches light, turns it into nervous signals, and sends it to your brain for processing. You probably know that you have rods and cones in your eyes. Just as a refresher, we'll get on to the really nerdy stuff in a second. The rods basically capture most of the full frequency of visible light. You can think of the rods as black and white receptors. They're really good in low light. And in fact, animals like bats just have rods, and it helps them see in the dark. But it's not exactly like black and white. It doesn't capture blues, greens, and reds entirely equally. It has a bit of an uneven frequency response, catching greens better than blues or reds. So let's try to diagram this. Again, I'm just going to make a very simple spectrum here with reds representing the long frequencies, greens representing the middle frequencies, and blues representing the shortest frequencies. For these cones, the frequency response kind of looks like this. It captures blues, but not that well. It captures greens pretty well, and it captures reds, again, not that well. If you want to see how rods work in your own eyes, get some colored paper of different colors and put it in a really dark room. And if it's dark enough, you will not be able to tell the difference between the papers. I promise. That's because in those dark environments, your color receptors aren't active at all. It's only those rods, and they can't distinguish between the different frequencies of light. But this video is about color, so let's talk about our cones, which capture color. You've probably heard we have red, green, and blue cones, but it's not actually that simple. So let's start with the blue because those are the lowest frequencies. You have these blue structures in your eyes, which are called cones, and the external part roughly looks like that. They're not really that cone-shaped. And they're tuned to respond mostly to the blues, and then they fall off pretty quickly once you get into the greens. So yeah, they're more sensitive to certain frequencies than others, and they will pick up some green light. And that's absolutely necessary for you to be able to see a full spectrum of colors. Now we have our green cones, and they have a frequency response curve that looks kind of like that. So the green cones in the middle can pick up both blue and red, as well as green, but they don't respond quite as actively to the blue and the red. They mostly respond to the greens. And then we have red cones, which aren't really, just slightly shifted from the greens, and they go kind of like that. The world isn't just red, green, and blue, right? Between blue and green, you've got cyan, and between red and green, you've got yellow. So if we only have 3 types of receptors, how can we see those colors? Well, let's say between the green and the blue, you've got cyan here. There are 2 ways for our eyes to register cyan. The first is that we actually see light coming in on that frequency between blue and green. So light with a certain wavelength comes in here. Both the blue and the green cones in our eyes will pick up that light. And if a blue cone and a green cone are close together and they both see some sort of light, then your brain says, hey, I bet that's cyan. So I'm going to process that as cyan. There's another way though. If you happen to get both blue light and green light at adjacent cones in your eyes, your brain will process that as cyan, or some shade between those 2 colors depending on how much of each that you get. Now, do you understand why this screen looks yellow even though it's actually red and green? That's because when I look at it in person and I'm not super close to it, the red and green trick my eyes into thinking that it's getting a color somewhere between red and green. Or really, it's just how my eye represents both red and green at the same time. There is no yellow. Now let's talk about how cameras work. Now, if you're a camera designer and you wanted to make the perfect sensor, you would say, I'm going to build this thing that just catches all the light, and it measures the direction that the light is coming from and the precise wavelength. And then I'll measure those wavelengths and turn those into individual colors that'll make a perfect picture. But we just kind of can't do that. We don't know how to do it yet. But what we can do is we can make sensors that capture light in big grids. So let's start out with a grid. Now, if you were trying to find a way to represent color to human beings, you might start with a model that kind of works with the eye. So this is a grid of photosites. Each one of these is capable of capturing light. And you could just stick a filter on there that only allows visible light through, in which case you would end up with a black and white sensor, a monochromatic sensor like in the Leica M. That can be cool, but you might also want to take color pictures. So what you do is you dedicate one of these photosites to blue, you dedicate one of these photosites to red, and then you dedicate one of these photosites to green. Now, if light on the green frequency comes in, only this particular photoreceptor lights up, and the computer can process that and say, oh, okay, I have green, but I have no blue or red, therefore the color is green. If we get both green and red coming in, then the computer processing it can say, hey, in this group of colors, I received both green and red. Therefore, I'm going to make that color yellow. It works exactly like your eyes. And if you look at the real frequency response for the red, blue, and green, it almost exactly matches the frequency response of your eyes. So yeah, the green photo sites will actually capture some blue and some red. That kind of depends on the camera. And in fact, some cameras like Phase 1 and Hasselblad, like super high-end, like $10,000 cameras, will brag about their color response and color science by just tuning each of those photo sites a little bit differently to have a little bit narrower ranges, which might allow them to have more precise color. That's kind of high-end color science stuff. Now, so far we have 3 of those photo sites used, but the 4th one is doing nothing. So we should do something with it, right? Today, almost all modern cameras that aren't Fuji handle it the same way. In 1974, Bruce Baer was working for Kodak, who would develop the very first digital camera, and he was the one figuring this out, and he came up with the Baer filter. And it looks like this. This 4th quadrant goes to green. So we have 1 red, 1 blue, and 2 green. Why is that? Well, if you remember from the previous chart, the greens pick up the most light because they're in the middle. So by picking up more light and having 2 of those greens, you're making it a little more sensitive to light, which is a good thing. And in general, human eyes are more sensitive to green than the other colors, but mostly I think it's probably just because it's in the middle of the frequency, and that's kind of useful. We call this the RGB filter for red, green, and blue. But it's not the only option. One that I think we're gonna see a lot of in the future that is really cool is RGBW. And that 4th quadrant here is left open. It just catches anything in visible light. And that means it's collecting way more light than just green would. And that means that the sensor itself is more sensitive to light, and that in turn means that the sensor can be much cleaner. Some RGBW sensors are already in production, but for the most part, they haven't made their way to professional cameras yet. It seems like people are still figuring out the most effective way to de-Bayer this. Though it wouldn't be de-Bayering, it would be de-mosaicing. That's the process of taking the information from each of these pixels and figuring out how to make an actual picture out of it. Okay, let's revert back to the very common Baer filter and extend it a little further. Because what I gave you so far is just 1 pixel, and cameras have megapixels, millions of pixels. So let's draw it out for another box. The greens will continue in this diagonal. Literally every other photo site is green, and then the others alternate between red and blue. So a little vocabulary here. Each one of these cells is a photo site. Photo sites capture red, green, or blue. Though again, when I say that, they're not perfect, but they capture quite a bit of detail and overlapping colors. That's a photo site. A group of 4 photo sites provides the information you need to create a pixel in the resulting photo, because 4 photo sites are the only way to gather complete color information. But adjacent pixels share photo sites. So these center 4 photo sites that I drew at first are actually participating in 9 different pixels all around the edge. This Baer filter right now, it's the best we have, but it's far from perfect. After all, if you're photographing something that's only blue, that means only the blue photo sites are picking up any information. And that means that blue light that falls on the green photo site here is completely lost. Blue light that falls on the red photo site, completely lost. Therefore, you're only gathering 1/4 of the light if you're photographing a red or blue subject, and you're only gathering about half the light if you're photographing a green subject. And as we know, if you watch my ISO video, the more light you gather, the less noise the picture has. So we're ending up with noisier pictures. So why can't we develop a system where each photo site collects all the light? Well, we kind of can. It's called a foveon sensor. Each pixel in a foveon sensor kind of looks like this. This is the side view of the pixel. This is where light is streaming in. At the top we have a thin filter of blue. Why is it thin? Because remember, the blue lights have the shortest wavelengths. Then we have a thicker filter of green in the middle wavelengths, and then we have the fattest filter at the bottom the longest wavelengths. And this kind of makes sense if you've been paying attention, because remember, longer wavelengths are better at penetrating through things like buildings, whereas shorter wavelengths tend to get caught. So that's kind of how it works. Unfortunately, it doesn't work that well. These photosites, they have to be bigger and they're not that efficient. And the reality is Sigma, the company that owns Foveon, hasn't made it take off. They have produced a couple of cameras with Foveon sensors, and they are kind of cool, but we just haven't seen widespread adoption. As an alternative, we do have our technologies that shift the sensor around, moving it exactly one photosite between each picture so that every location on the sensor is able to capture red, green, and blue data, and then it stacks it together. That technology has a fundamental flaw because those pictures have to be taken at different points in time, and thus things can move during that period of time, and then you have to figure out a way to handle the movement, and nobody's really done a good job of doing that. Besides the Bayer filter, there is one moderately common alternative used only by Fuji at this point, which is the X-Trans sensor. So let's draw a little bit bigger grid of photosites here. The X-Trans sensor uses green even more heavily than Bayer does. With the X-Trans sensor, we have 4 green pixels kind of crammed together. And then pixels on their diagonals are green. And then off of each one of those, we have more green sensors. And you can see the X-Trans sensor is mostly green. Let's fill in the red and the blue. Because the green photosites are a little more sensitive to light, the X-Trans sensor actually has a little bit of advantage for noise. But the color accuracy can actually be so bad that it causes some problems. After all, imagine that you're taking a picture of something that's red. The algorithm that collects all this data and turns it into a picture only has these handful of red photosites to rely upon. And there's some pretty big gaps in here. If red is falling in here, it can't see it at all. And so if these 4 photosites that collect red all fire up, the demosaicing algorithm will generally assume that this whole center portion here is red, but it might not be. And one common side effect of this is you'll photograph somebody's face, notice red lips around white teeth. What will happen? The teeth will end up red. Because the algorithm has to make guesses. It does not have information about those colors. This is a kind of a software thing, but the algorithm can only be as good as the data put into it. Garbage in, garbage out. In the real world, though, we shoot with Fuji all the time, and in fact, this overhead camera is shot with a Fuji, and it's not much of an issue. Oh, one more thing. Imagine that you were photographing something black and white, like text on a page. Let's say we had this long line that kind of ran through here. If this line is white, it's producing light that is caught by all of the pixels, because white is made up of the entire frequency of light, red, green, and blue. So white is lighting up all of these pixels, but what the sensor is seeing is green, blue, green, green, red, blue, green, blue, green. Thus, if the line is small enough, the demosaicing algorithm can be confused and might interpret it as having color along the edges. This is called false color or moire, and in the real world it happens pretty frequently with fabrics and such. So if you were a sensor designer and you wanted to prevent that from happening, what you might do is try to blur everything. After all, if this white line was passing through here and it was blurry, now that thin white line is setting off photosites of all these different colors, and that's giving the algorithm the information it needs to determine that it's actually white, because the light is being cast around a little bit more. So that's why some sensors have what's called anti-aliasing filters or optical low-pass filters. They literally just blur the incoming light in order to spread it around and make sure that it hits photosites of red, green, and blue, reducing the occurrence of moire. So the anti-aliasing filter is there for a good reason and should be helping, but at the same time, its intention is to blur the picture some. And if you're trying to take really sharp and highly detailed pictures, that can be a bad thing. And that's why manufacturers make cameras both with and without the anti-aliasing filters. For example, Nikon made the D800, which had an AA filter, and the D800E, which did not have an AA filter. And if you were a wedding photographer, somebody shooting fabric all the time, you would probably pick the D800. And And if you were somebody who wanted peak sharpness and you were willing to deal with a little moire, perhaps manually removing it in post, you would pick the model without the AA filter, the D800E. This has been a lot of information, I know. I hope it helps you understand the entire process of taking pictures as well as how you perceive color in the world around you. If you like this stuff, be sure to subscribe, and if you just want practical photography tips, wait, let me get something. Check out my book, Stunning Digital Photography. It's the #1 photography book in the world, and I promise it'll do a lot more to improve your photography than understanding the details of bare filters. If you want more nerdy stuff, we have an entire playlist on our channel filled with these geeky topics. If you have follow-up questions or if you think I've made some mistake, add a comment down below. Bye.
I'm going to blow your mind one last time. Purple is not on the rainbow. Literally, it is a non-spectral color. Here's what that means. This is the visible color spectrum, and you probably learned Roy G. Biv, red, orange, yellow, green, blue, indigo, violet. But notice there's no purple on there. You can see yellow is located right between red and green. There are two ways the human eyes can see yellow. Either we can pick up light that matches the frequency between the red and the green, or our eyes can see both red and green light coming from very close to the same place, and our brain will trick us into thinking that it's yellow. So how does purple go about? Because purple is between red and blue, but there is no wavelength directly between those two. If you look at the color wheel here, you can see between red and blue is purple, but on the visible spectrum, there is no in between because they are on opposite ends of the visible spectrum. We only see purple as a mix of red and blue light. There is no matching wavelength for purple. Purple is totally made up in your brain. That's it. Don't forget to subscribe. Bye.